Hello, welcome back to our conic sections material. Today we're going to look at my second favorite conic section. My first favorite is circles, but don't tell the others that. My second favorite has to do with ellipses, plural for ellipsis. You know, we're going to be looking at ellipses. We're going to be looking at different examples of those. So that's where we're heading now. So like circles and parabolas, it's a set of points on a plane, and it makes an ellipse is a shape. I showed you in a previous video, like when you cut through a cone with a plane, like a flat surface, that cross section, what it looks like for an ellipse. But let's look at a formal definition. Kind of in general, an ellipse looks basically like a flattened circle. But how can we define an ellipse? It's the set of all points in a plane the sum of whose distances from two fixed points is constant. Each fixed point is a focus. If you want to talk about them in a plural form, you got foci of the ellipse. Okay, so you're just drawing a rough sketch of an ellipse. The little rough sketch I just drew, imagine as being like a nice flattened circle. All those points that make up that ellipse. If you identify the foci on this ellipse, it kind of looks like a flattened robot head with eyes when I put the foci in there. Like, let's say you have foci 1 and foci 2. When you identify the foci, you could take any point on the ellipse, and the distances from that point on the ellipse to those foci, the sum is a constant. So you could go around and pick any point on the ellipse, and this is going to be true about those distances from that point to those foci in the sum. Notice that this is not a function. If you try to do the vertical line test, it's going to fail very quickly because sweeping it across, except for like the far ends, your vertical line is going to be going through 2 points at a time. So, but it is a conic section. All right, so let me identify some different pieces to this so that you can know what we're talking about. Again, I'm just doing a very rough sketch here. Sorry, I'll try to do better later when we're actually graphing things. But on the ellipse, you're going to find that it's wider in one direction and narrower in another direction. That wider direction, you have the major axis that goes from one extreme point to the other. And in that narrower direction, you have the minor axis. They intersect at right angles there. Your foci are going to be located along your major axis. So you have 2 focus points. Those foci will be located along those. The major axis is always the longer one. So even if your ellipse is oriented differently, like let's say it's oriented this way, then in that case, your major axis would be going, that longer one, and then your minor axis would be the shorter one. So and again, the foci would be along that major axis. So that's something to keep in mind as well. You got the center of the ellipse. That's where those two intersect. Those two axes. So that's the center. And when you're, and what else? So, vertices. If they ask you about a vertex, the vertices are the endpoints of the major axis. So those two are vertices. Or even if it's oriented the other way, you're looking at your major axis, that longer axis. Those 2 points are going to be your vertices. Okay, so we addressed major axis, minor axis, foci. The midpoint of the major axis is the center of the ellipse, but that's also where those two axes intersect each other. Endpoints of the major are the vertices. This is not a function. Fails the vertical line test. All right, so that's a lot of the main terminology that you're going to need to remember as we're working on these. Okay, so what can we do next? Now next we can develop the equation for an ellipse. The equation is going to have a certain form to it. Let's say you have an ellipse that is centered at the origin. And again, I'm just going to draw a rough sketch of one. Okay, so let's say it's centered at the origin, 0, 0. We don't know exactly where the foci are, but the distance from the center to the focus is going to be called C. So like the focus on the right there is at C, 0. The focus on the left is at negative C, 0. And they go ahead and call that focus on the left like F prime. So that distance there is C. And then we use a lowercase a when we're talking about the length for the major axis. So the vertex on the right is going to be at A0. Vertex on the left is going to be at negative A0. And when we talk about the lengths for the minor axis, we use a lowercase b. So that point at the top end of the minor axis would be 0b. Point at the lower end of the minor axis would be 0, negative b. And then you'll find that, okay, so they went ahead and named that point up there capital B, this point down here capital B primed. Yeah, vertex B and vertex V primed. So just a couple of things to keep in mind. And then let's say you have some other kind of random point on this ellipse. We'll just call that point P, and it's going to have some kind of coordinates x, y. And we're going to be looking at what's going on when you're talking about distances from a point P on the ellipse. Now remember, according to definition back here, a point on the ellipse, the sum of the distances from that point to the two foci, it has to be a constant. So we're going to use that fact and write up a little observation here. Okay, what if we look at point P as being located where we have our vertices? That's a nice convenient place to really talk about. Like if your point P was right here at this vertex, then you can look at your distances and figure out like a length pretty easily. Let's see. We know that the distance from point P, the distance between point P and one of the foci, plus the distance from point P to the other foci has to be a constant. But what could that constant possibly be? Well, if you imagine point B as being where I made that red X, that would actually come out to 2a. And since it has to be consistent all the way around the ellipse, it doesn't matter where point P is located, it was still equal to 2a. Because if you look at where A is right now, like if you look at this red X, you've got the distance between the red X and F. That's the same as the distance over here between V primed and F primed. And if you added that with the distance from V to F primed, you end up with double the A, or in other words, the length of that major axis there. So it turns out if you pick any point on the ellipse, your distance, the sum of the distances to those two foci is going to give you the same as that major axis. Okay, but you can use that, you can use your distance formula and work some things out. You know that your distance from P to F would be the square root of x minus c squared plus y squared. And you know that your distance from P to F primed would be square root of x plus c squared plus y squared. And if you go ahead and add those together, it's going to equal 2a. Well, you can do some algebra. I'm not interested in working out this algebra for you. But after some algebra, I mean, if you want to, you can reference in the current textbook, page 1002, does this algebra, and you can see it. But you end up with x squared over a squared plus y squared over a squared minus c squared equals 1. So you're almost there. You're almost to that general equation that we need for an ellipse. Now to clean it up a little and deal with this a squared minus c squared, you can use point capital B there and talk about what's going on with it. You could do the distance from B to focus F plus the distance from B to focus F primed. And again, that has to equal 2a because B is a point on the ellipse. So the distance from that point to one focus plus the distance from that point to another focus is also going to equal that 2a. So remember from earlier, any point on the ellipse, some of the distances from that point to the foci is going to basically equal the length of your major axis. So, come on, I'm tapping you. Why aren't you changing? Thank you. So you can do, again, some algebra there with distance, and you find out, so you do some more algebra, and if you're interested, just the next page over, page 1003, and you find out that b squared equals a squared minus c squared after you do that algebra. So you can now write your equation as x squared over a squared plus y squared over b squared equals 1. And that's going to be the standard form of the equation of an ellipse centered at the origin, with foci right now on the x-axis. Now, if it's on the y-axis, what happens is your a and b switches. But I'll draw like a summary here. All right, so first of all, let's say you have your ellipse like this. Okay, you have negative a, and you have b, negative b. Your foci have to be on the major axis, and then this is at 0, 0. If you have no, and this is centered at the origin, the equation's x squared over a squared plus y squared over b squared equals 1. So the vertices in this case are at plus or minus a comma 0. So a 0 and negative a 0. The endpoints of the minor axis are at 0, plus or minus b, so 0, b, and 0, negative b. The foci are at plus or minus c, 0, because those are on the major axis. And we know that c squared equals a squared minus b squared, which will be very important as you're working things out. If you know the focus, or if you don't know the focus, that formula is going to help you out. Now you could also, if you switch your ellipse and have the major axis running vertically like this, then now the A's will be along the y-axis, and then the B's will be on the x-axis. So A is going to always refer to the major axis. So if it's oriented differently, then you're going to have to switch. So now the formula, instead of having A under x, it's going to have B under x. So x squared over b squared plus y squared over a squared equals 1. So then it all switches out. Oh, and I forgot to add, A is going to be greater than B every time, because we're situating A along that major axis. So in this case, all right, you got your 0. Let's see. So this case, your vertices will be at 0, plus or minus a. So notice the change in the way the order pairs are written. Endpoints of the minor axis at plus or minus b, 0. So notice that swapped x and y also. Foci, 0, plus or minus c. And again, c squared is equal to a squared minus b squared. So that formula, you do the larger a squared minus the smaller b squared. And that equals c squared. Okay, so what do we want to do next? How about we actually graph an ellipse? That's probably the next thing to do, like actually take one and work on graphing it. So let's say we're given the equation 4x squared plus 25y squared equals 100. And we're asked to graph it. Now you might notice in the formats of the equations up here, each time the equation's equaled 1. So let's get it into that standard form. Let's make sure this equation equals 1. So we're going to have to take that 100 on the other side of the equal sign and divide both sides of the equation by it so we can accomplish that 1 that we need. So we'll have 4x squared over 100 plus 25y squared over 100 equals 1. Do a little reducing. X squared over 25 plus y squared over 4 equals 1. So we indeed have an ellipse. We're able to get that equation into that standard ellipse form. On this ellipse, the 25 is bigger than the 4, so the major axis must be along the x-axis. And right now we're going to be centered at 0, 0. We'll talk later about how it looks when it's centered elsewhere. But a squared is 25, which means a is 5. So the distance from the center to a vertex will be 5, going opposite directions there. B squared is 4, so b is 2. And then we know c squared is a squared minus b squared. So 25 minus 4, which is 21. So for c, we're going to be dealing with square root of 21. So that tells me that the foci are located at negative square root of 21 comma 0 and positive square root of 21 comma 0. That's where the two foci are going to be located. All right, and then once you have that information, graphing it's not too much of a stretch. Okay, we're centered at 0, 0. Since A is 5, then we need to go 1, 2, 3, 4, 5 out to the right from 0, and 1, 2, 3, 4, 5 to the left from 0. So vertices there. So that's going to be in those ends of the ellipse. And then since B is 2, we're going to go up 2 from 0 and down 2 from 0. So that's the endpoints of our minor axis. And once we have the vertices, or endpoints of the major axis, and then the endpoints of the minor axis, we can just go ahead and connect the dots with a nice, as good as we can, drawing a nice flattened circle, kind of a football shape, basically. So the foci being plus or minus square root of 21, or what's that as a decimal? Let me see here real quick. Using a different calculator. Hang on a second. All right, so I'm getting around 4.6. So square root of 21 is around 4.6 roughly. So then on your graph, one of the foci would be there, and one of the foci would be there. So the flatter or the less round your ellipse, your foci are going to be closer to those vertices. The more round your ellipse, like the closer to a circle it gets, the more your foci move in towards the center. And in a circle, your foci, technically your foci is the center. So we'll get to that in a little while when we talk about something called eccentricity. One other thing they're going to ask you probably on these questions is what's the domain and range? So, domain, this thing's nice and smooth. It's not a function, but it is a relation. It's a set of ordered pairs. So we can identify domain. How far left, how far right? Well, extreme left is -5. Extreme right is 5. It includes those points. It has nice, smooth, no gaps, no overlaps in between when you're tracing it. And the range, how far down, how far up, goes down to -2 and up to +2 on the y-axis. So that's your domain and range. All right, let's graph another one. This time we're going to have the major axis along the y's. So we're going to have this one, the equation is 49x squared plus 9y squared equals 441. Okay. And it's going to work out notice that on this one, the number in front of y right now is smaller, but it's going to end up working out so that the number underneath is bigger. So our major axis is going to be along the y-axis. We're still talking about a center at 0, 0. Okay, so put everything over 441 so that we can get that 1 over there on the right of the equal sign. Let's see. Reduce, you will have x squared over 9 plus y squared over 49 equals 1. So in this case, a squared is 49, so a is 7. Hopefully I don't make the mistake earlier. There's so many 9s in this problem that when I was first working this out, I was trying to use 9 instead of 7, so I hope I don't make that mistake again. My brain, I have a son brought home a cold from school and I'm dealing with that this weekend, so my brain's not totally there. All right, so a is 7, 7, 7. Gotta make sure I don't make that mistake again. All right, so we've got our B, identified our B, identified our A. C squared is A squared minus B squared. So that would be 49 minus 9. Notice that it's always the larger minus the smaller. That equals 40. So C, we're dealing with the square root of 40, which is the same thing as 2 square roots of 10. So our foci this time will be along the y-axis. So at 0, -2 square roots of 10, and at 0, comma, positive 2 square roots of 10. That's where the foci are. You know, let me do a real quick calculation of what the square root of 40 looks like. Square root of 40 is approximately 6.3. So that'll be interesting when I go to graph this thing. Okay, let's graph it over here. I should have plenty of space if I do my axis here. I hate how sloppy this ends up when I'm drawing on this tablet. I should pull out a straight edge and use it, but I've been too lazy. Okay, so A is 7, so along the y-axis is our major axis. 1, 2, 3, 4, 5, 6, 7. So we got to go up to 7 there. Then 1, 2, 3, 4. You know, oh my gosh. You know, I'm going to cut this in half because I don't like that. You can't even see what I'm doing up there. So let's do this. Let's go 1, 2, 3, 4, 5, 6, 7. Let's do it like that. So that way I can have it all on the same screen and not have to scroll to see the graph. All right. So 7 there. 2, 4, 6. Negative 7 there. And I did not make that mistake of accidentally using 9. Yay. 1, 2, 3 there. And 1, 2, negative 3 there. And connect your dots. So the vertices are at 0, negative 7, and 0, positive 7. And then the endpoints of the minor axis are at negative 3, 0, and 3, 0. And then talking about the foci being around 6.3. So 6.3 and negative 6.3. Foci are still going to be along that major axis. Okay, what else did we have to identify? So we did the ellipse. We have the coordinates of the foci. And finally, we did not do domain and range yet. So domain, that's still your x values. So it goes from negative 3 to 3 with brackets because those points are included and everything in between is included. And then range, we'll use negative 7 to 7. Goes down to negative 7 and up to positive 7. And there you have it. Okay. So that's graphing two different, an ellipse, these ellipses are centered at 0, 0, or the origin. One of them was oriented along the x-axis with its major axis, and then the other one's oriented along the y-axis with its major axis. You might have noticed a pattern. We learned about equations and graphing, and then we learn, well, how do we write the equation? So that's going to be my next example. Oh my goodness. I was trying to write E and I wrote H. Why? Write an equation of the ellipse. I feel like these are easier than parabolas when you're writing the equations. With center at origin. So we know 0, 0 is the center. Foci, they gave us the foci on this one at negative 5, 0. Oh, the foci are situated on the x-axis. So that tells me the major axis is along the x-axis. And they tell us the major axis length. Okay. So we're trying to write the equation of this ellipse. Given that information, I like to kind of sketch a bit just to really get me an idea about what's happening with this ellipse. So again, I'm not going to like situate it just right on the grid, but they tell me my foci are at negative 5, 0, and 5, 0. So, you know, like somewhere over here, like this. And then they tell me the major axis length is 18 units. Actually, that tells me a lot. If major axis length is 18 units, then A has to be 9. It has to be half of that. Because remember, you know, you got A over here and negative A over here. So A is 9. C is 5, based on that. And we know C squared equals A squared minus B squared. So C squared, or I should say 25 equals 81 minus B squared. So B squared equals 56. I don't really need the square root of that, but I mean, if I did, you know, that would tell me what's going on here and here. So really at this point, I think I have everything I need because I know that the equation is going to be in this format. X squared over A squared. So major axis A is going to be under X in this one. Plus Y squared over B squared equals 1. So I know A squared is going to be 81. I know B squared is 56. And it has to equal 1. And that's all I need. I don't really have to do any more. I mean, because that's all that this question asked me to do. So there we have it. There's the equation. All right, and one other oddity before we get into ellipses that are not centered on 0, 0, is what if you're graphing a half ellipse? That happens sometimes too. Let's say you're given the equation y over 3 equals negative square root of 1 minus x squared over 4. Okay, right now that negative sign right here is something to think about. This is telling me that since the y over 3 has to equal a negative, then it's telling me it wants like the bottom half of the ellipse. It wants the part where all the y values are negative. So when I go to graph it, I'll just need to remember that. But let's work it out so that we can get the equation into that standard form that we're familiar with. So let's square both sides. But notice when we square both sides, suddenly that negative sign isn't there anymore. So that's why it's important at the beginning to kind of think about what's going to happen later when we graph this. Add x squared over 4. And we've actually got our equation now in standard form. 9's bigger than 4, so A is going to be 3, B is going to be 2. So when we go to graph this thing, the major axis is along the y-axis because the 9's underneath the y squared. So we know we got to go down. We got negative 3, we got positive 3. Then for the minor axis is going to be along the x-axis. So we got positive 2 and negative 2. Again, this is centered on 0, 0. And then since we're only dealing with the half that's under the x-axis that has the negative y's. So we're only dealing with this half right here. And that's it. Because of that negative sign where the y over 3 equals a negative. If you hadn't had if it had been plus or minus, if it had the plus minus sign, then we would know it wants the whole thing. And in fact, if you're using a graphing calculator, that's something to remember. If you want to graph the entire ellipse, you got to solve for y, put like the positive square root in for y1, and put the negative square root in for y2, and that way you can get the full ellipse. If you use Desmos, you don't have to worry about that. You can put the entire equation in as normal. You don't have to do the whole square root thing. So, if you have trouble with that, let me know. But Desmos is a lot easier. You don't have to break it apart like that. Okay. Oh, it also asks for domain and range on this one. They love asking for domain and range on these problems. So domain would be from -2 to 2. And then range would be actually from -3 to 0 on this one, because it's only that bottom half. All right. Now what if we take an ellipse and we decide to shift it? Well, our equations are going to look a little different. But it's kind of like when you're dealing with circles. Like when a circle is centered at the origin, you have x squared plus y squared equals some number, like 25 or something, the r squared. But once you have your circle centered elsewhere, you have x minus h squared plus y minus k squared equals r squared. Our ellipses are very similar. If you have x minus h squared over a squared plus y minus k squared over b squared equals 1, then you have an ellipse with the center at hk. And then your a is still the length of your center to one of your vertices. And your b is still the distance. The absolute value of b is still the distance from the center to your endpoints of your minor axis. And then if it's situated the other direction, like this, with hk in the center, then it's still x minus h squared. It's still y minus k squared, except your b's and a's are switched. So it looks a lot like the other equations, just you have that h and k in there to dictate where the center is. Let's look at how we would apply that to help us graph ellipses that are not centered at the origin. Okay, let's say we need to graph x minus 3 squared over 36 plus y squared over 9 equals 1. And later we'll have to get the foci, domain, and range. All right, so our center, in this case, is going to be at 3, 0. Because our h is 3, and then since there's nothing subtracted from y, the k is 0. A is 6, b is 3, square root of 36, square root of 9. C squared is still a squared minus b squared. So 36 minus 9, which is 27. So for C, we're dealing with the square root of 27, or 3 square roots of 3. All right, so when we go to graph this, make sure I've left myself enough space here. Let's see here, 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3. Yeah, I think I have enough space. I think I'm good. All right, my center is at 3, 0. So right here. Now this A being 6 means I have to go 6 units from the center. So to find my vertices, I have to go 6 units to the right of 3, which will land me at 9, and 6 units to the left at 3, which will land me at -3. And then for the minor axis, B is 3, so from 3, 0, I'm going to go up 3 and down 3. And then connect my dots. Notice that I haven't really spent time trying to find all the y-intercepts and everything. Honestly, you don't have to unless it asks. As long as you have those endpoints for your major axis and minor axis, you're good. Now your foci aren't going to be at plus or minus 3 square roots of 3. Your foci are going to be at 3 minus 3 square roots of 3, comma 0, and 3 plus 3 square roots of 3, comma 0. So wherever that lands you, find decimals help for me. Because you have to start with at 3 and go to the left 3 square roots of 3 units and go to the right 3 square roots of 3 units. Square root of 27 is around 5.2. So you got to go to around negative 2.2 for one of them. And you got to go to around 8.2 for the other, for the two foci. Your domain, well, notice you take the center, like since A is 6, 3 minus 6 gives you negative 3. 3 plus 6 gives you 9. For the range, your center's at 3, 0. So 0 minus 3 gives you negative 3. 0 plus 3 gives you 3. And there's that. All right, so we have our foci, we have our domain, we have our range, we have our graph, all this good stuff. Yeah, so there you go. So that's what happens when your center is in a different place. Okay, what if we need to take an equation and get it into standard form? And it looks kind of messy to start with. Like it's not gonna be one of those with center to the origin, so it's gonna be a bit messy. And here's an example of such a thing. The one earlier was centered at the origin, so we were able to just do like pretty much a quick division and get it to where we need it. But notice this one has an x squared term and an x term and a y squared term and a y term. So we're going to have to do some completing the square to help us do this, to help us get it into that form that we need to identify everything and graph the ellipse. So for the x terms, those are already grouped together. That works. I'm going to factor out the 4. So I have x squared plus 6x. I'm going to leave a little space because I'm going to need to be able to complete the square on this. Then y squared minus 8y, I don't really need to factor out anything. But I'm going to go ahead and put a plus 1 there just for reference later, just in case I need to think about it. You might not need it, but. All right, completing the square, x squared plus 6x. I take half of 6, which is 3, and I square that and get 9. But if I'm adding 9 in the parentheses, that's really like adding 9 times 4 outside the parentheses, so that's like adding 36. So I need to add a 36 over here on the right to keep it all balanced. Then for the y's, half of 8 is 4, squared is 16. 1 times 16 is 16, so I need to add a 16 down here to keep it balanced. Do a little factoring. Since I completed the square, I have perfect square trinomials. And then on the far right, just combine your terms. 12 and 36 is 48, plus 16 is 64. So this is working out pretty nicely. So far, so good. And then now I'm going to focus on getting that 1 on the right that I need. So I'm going to divide everything through by 64. So I'll have x plus 3 squared. And then 4 over 64, it's going to reduce down here to 16. then y minus 4 squared over, that's because it's still going to be 64 because there's a 1 up there, and then equals 1. Yay! All right, apparently the major axis is along the y's, along the vertical direction, because 64 is bigger than 16. So I could see that a is going to be 8, or the square root of 64. I could see that b is going to be 4, square root of 16. C squared equals 64 minus 16, which is 48. So for C, we're going to be dealing with 4 square roots of 3. But honestly, it didn't ask me to find, interestingly, it didn't ask me to find the foci, but it asked for the center, the vertices, and the endpoints. Anywho, and then the center is at -3, 4. So the signs are opposite of what you see there with the x and y. So center's at -3, 4. So then if you were doing that, oh my goodness, I'm going to need to probably go by 2's just to squish it all in. This is getting to be some big examples. And so if I go by 2's, -3, 4 is right here. A is 8. So we're going to be there. Which is at 12. And then we're going to be there, which is at -4, because A is 8. So our vertices are at -3, -4, and -3, 12. Because the vertices are along that major axis, the x value is -3. And then you take the y value 4, you can, from the center, you can subtract 8 and get -4, or add 8 and get 12. And then for the minor axis, okay, the 4 part from the center, the 4 part's going to be the same. B is 4, so we got to go 1, 2, 3, 4 to the right. So we end up with 1, 4. And we got to go 1, 2, 3, 4 to the left. So we end up with -7, 4. And you can connect your dots to make your nice football shape. Well, not really quite a football. Footballs are pretty pointy on the ends. But a nice ellipse. It's not an egg shape either. An egg is a different shape. It's not an ellipse either. All right. I have to look at rugby balls. I wonder if they're more closer to elliptical than footballs. Not as much. Anyways, maybe I'll look that up later and find out. Maybe. Not promising. So the foci, we were looking at the 4 square roots of 3. Let's see here. Square root of 48 is 6.9. So you would go like 6.9 up from the center and 6.9 down from the center if you're wanting to find your foci there. But it just asked us for the center, the vertices, and the minor axis points. So there you go. All right. Finally. Let's do a little bit on eccentricity, and then I got a couple of word problems. And then that'll wrap this up. And this is turning out to be a long one. These conic sections are long. That's why there's not as many sections in the calendar for a longer period of time. These are long. Let's talk briefly about eccentricity. A conic is the set of all points P of x comma y in a plane such that the ratio of the distance from P to a fixed point and the distance from P to a fixed line is constant. We already addressed this in a previous lesson with our parabolas. With our parabolas, we talked about our directrix and our focus. And we talked about how your distance, like from any point P on this parabola, you could go perpendicularly to the directrix, that distance, or just from P to the focus, that distance. We talked about how those distances are the same. So we talked about how the distance between P and F is the same as the distance between P and D. P in the directrix and P in the focus. So the eccentricity, we write E, lowercase e is eccentricity. Don't confuse this with like base of natural logarithms, like log base E. Totally different E. In this case, we're using E because of the word eccentricity starts with E. That's it. But in this case, the eccentricity is that ratio. If you put D, the distance from between the point on the parabola and the focus, and do a ratio with the distance of that point and then the directrix, then that's going to come out to 1 because they're both the same number according to the definition of a parabola. So the eccentricity of a parabola is 1. For an ellipse, this eccentricity is a measure of its roundness. In an ellipse, the eccentricity is C over A. So the same C and A that we've already been talking about. C is the distance from the center to the focus. A is the distance from the center to the vertex. By our definition of an ellipse, we know that A squared is going to be greater than B squared because we define A to be along the major axis, B to be along the minor axis. We also know that C squared is the square root of A squared or C is the square root, not C squared. Square root of A squared minus B squared. So we know that 0 is less than C less than A. You can say 0 is less than C over A, which is less than 1. So the eccentricity of our ellipse is going to be between 0 and 1. So every ellipse has a eccentricity between 0 and 1. So if your A is constant, if C gets closer to 0, gets closer to the center, that's going to force the ratio C over A to approach 0. Also forces B to approach A, and so forth. So, and then if the eccentricity approaches 1, B will approach 0. So it's kind of interesting. The more for the eccentricity, the smaller the value, the closer to 0 it is, the more circular your ellipse is going to be. The closer to 1 it is, the more like stretched out your ellipse is going to be. So like if it's more circular, your two foci are going to be closer together. If it's more like stretched out, you're going to have that bigger eccentricity and your foci are going to be spread out more. So it goes along with that ratio with the C and A. So if your ratio of C over A is smaller, approaching 0, you're going to be more round. If your ratio of C over A is bigger, approaching 1, you're going to be more stretched out, like elliptical. And in fact, if you take the equation of a circle and look at it and find out that circles have eccentricity of 0. So that eccentricity got pushed all the way over to 0, then you have that perfect roundness of a circle. So that's just a little something about what eccentricity is for an ellipse and about the roundness. Now you're going to be asked to compute eccentricity. So let's say you're given the equation of an ellipse that looks like this. And you want to find the eccentricity. Well, you know here that B is 9 and that A is 10. Because the bigger number is underneath the y squared, smaller number is underneath the x squared. So A is 10, let's do the square roots, you get 10 and 9. You need C. So A squared minus B squared is going to give you C squared. So 100 minus 81 gives you 19. So C, you're going to be dealing with, square root of 19. You just do positive C over A. So you do square root of 19 over 10. And then eccentricity is going to be that, which is approximately 0.44. So that's close to a half. That's close to being in the middle there. But it's a little bit more on the rounder side because it's on the side closer to 0. Something like x squared over 11 plus y squared over 6 equals 1. Same idea, just you're trying to find C so you can do that ratio of C over A. In this one, you can see that A is going to be square root of 11. B is square root of 6. So 11 this time, the bigger number's underneath the x this time. C squared is going to equal 11 minus 6, which is 5. So C is the square root of 5. So eccentricity is C over A. So square root of 5 over square root of 11. If you put it in your calculator, you get your decimal. That's what these problems are going to probably ask for. You get around 0.67. So that's on the side of 0 closer to 1. So your ellipse is going to be more stretched out compared to the one on the left. So closer to 0 you get, the more circular you are. closer to 1 you get, the more like stretched out and flattened you are. The foci more circular you are, the foci are closer together. The more stretched out you are, the foci are further apart. All right, ready for some applications? I know that's the thing everybody's like, I need to see more word problems. Not that you want to do more, but you want to see more for examples. And these word problems are pretty cool because they help you see directly some practical applications. If any of you are thinking about ever working for NASA, you might want to perk up and think about really learning these conic sections solidly. Because when they're sending off aircraft into space, or NASA or Blue Origins or SpaceX or whoever, I know SpaceX has been sending a lot up lately, they do have to consider orbits and shapes and influence with gravity, etc. So they do have to know a lot about ellipses. Because the orbit of Jupiter is an ellipse. Sun is at one focus. Eccentricity of this ellipse is 0.0489. Max distance between Jupiter and Sun is 507.4 million miles. And we want to find the closest distance. For Jupiter and the Sun. Okay, so we can draw a little image to help us visualize what's happening here. Okay, so I'll use J for Jupiter, S for Sun. Man, I wrote that so fast I spelled Sun S-O-N. S-U-N, not S-O-N. We know the eccentricity, which is C over A, is 0.0489. We also know that the maximum distance between Jupiter and the Sun, so this distance here, is 507.4 million miles. And then we're wanting to find what's the closest distance. Like if Jupiter's over here, what is that distance? Okay, so let's think about what we know then. Have to do a little algebra as we figure this out. So I already know C over A. Let's see, we think about where the center is, right there. Over here we have, that distance would be A. This distance would be C. Like the distance from the center to one of your foci, that would be your C. We know A plus C is the 507.4 million miles. So there's that. So that tells me that C is 507.4 mil minus A, if I just subtract A from both sides of that. Then go back to my eccentricity ratio. Well, if I know what C is, I can say, well, 507.4 mil minus A over A, so instead of saying C over A, I say that, equals to 0.0489. Multiply both sides by A, 507.4 mil minus A equals 0.0489A. Add A to both sides, 507.4 mil equals 1.0489A. finish solving for A by dividing both sides by 1.0489, and you get 483.74485756 million. You know, C is 507.4 mil minus A. So now you can put that 483.7 mil in, and you get C comes out to 23.65512444 mil. So up here, we found A was 483.7 mil. We found C was basically 23.7 mil. I'm just abbreviating it up there. And we're still trying to find this. So to find that, we can say, well, we know this entire distance over here is also A. So we can do A minus C. And that's going to give us 460.1 million miles. And there you have it. All right, another cool application. This one I actually got to try out when I went to DC a couple summers ago. I'm a middle-aged adult and I'd never been to Washington, D.C., so it was so exciting to go. And I got to actually test this for myself there. And then more recently, went to a science museum and got to test this next example. Same concept. It was really cool. My son and I, at the science museum, we were able to stand at the two foci of a ellipse and check out this, do an experiment and check this out. But if you have an ellipse, and let's say you have a person standing at one of the foci, you have a little person here, and let's say that they talk, then their sound waves, wherever they're at, will bounce off the ellipse and go straight to the other focus in that room. So if you have an elliptical room with, the walls are an elliptical shape, you can stand at one of the foci in that ellipse, talk however soft you want. The sound's going to, wherever it goes and bounces, it's going to bounce off the walls and go straight to the other focus. So if somebody's standing at the other focus, they can hear you, even if you're whispering. It's pretty cool, huh? So they call that a whispering gallery. The little blurb in the book says, a U.S. statesman, John Quincy Adams, was able to listen in on his opponent's conversations in the old House chamber or statuary hall because his desk was positioned at one of the foci beneath the ellipsoidal ceiling, and his opponents were located across the room at the other focus. So in the Capitol building, it's pretty cool. There's a room there where you can sit and check it out. So where the statuary hall is. So we were able to do that in the science museum. They had like an ellipse with elliptical walls set up, and my son and I were able to do that. But the actual application problem is through dealing with something called a lithotripter. I'm not entirely sure how to pronounce that. I'm reading it. Lithotripter. It's a machine that uses shock waves to crush kidney stones. You're placed in an elliptical tub, the kidney stone at one focus of the ellipse. A beam is projected from the other focus to the tub so that it reflects to hit the kidney stone. So you're sitting in the tub with your kidney at one of these foci, and then there's a beam being directed from the other focus. And then that beam will keep bouncing off all the walls and come and hit the kidney stone and break it up. So let's say that the ellipse has this equation, x squared over 40 plus y squared over 24 equals 1. And you're trying to figure out, well, how many units must the kidney stone and the source of the beam be placed from the center of the ellipse. The elliptical tub you're sitting in. So essentially, you're trying to find that little c value there. So you're trying to see that distance from the center to each focus. Okay, so in this one, we can see that a squared is 40, b squared is 24. So then c squared is a squared minus b squared. So you get 16. So c is the square root of 16, which is 4. So whatever the units are, if you're in this tub, they want your kidney sitting 4 units away from the center of the tub. And then on the other side, directly across from you, they want the source of the beams being placed 4 units away from the center of the tub. So you turn the beam machine on, the beams start bouncing off of the tub walls, and then come and hit your kidney and help break up your kidney stones. Pretty cool, huh? All right, well, there you go. There's a little bit of everything that you need to know about ellipses, including some application problems. So now it's time to turn over the fun to you. Hope you enjoy ellipses. I actually enjoy them quite a bit. Our next adventure will be into hyperbolas. I don't enjoy those as much. They're still cool, but I don't know. To me, they're not as fun as circles and ellipses. But anyways, don't take my word for it. Make up your own mind. Some of you might love hyperbolas. But thank you for joining me, and I look forward to seeing you again soon so that we can start wrapping up conic sections.